All right, so in today's lesson, what I'm going to be talking about is time plots. Now, just a little bit of vocab. Time plot is a numerical variable, plots each performance against the time at which it was measured in order to observe possible trends over time and departures from these trends. So basically, what we're going to be doing is we're going to be taking a numerical variable and observing it over a period of time that we want to see. Is there any trend? Is it going up in a significant fashion? Is it going down? Or is it just kind of like going up and down? There's really no clear direction that this data is taking. So the first example we're going to be looking at is Emmitt Smith. So how do running backs age? Typically, running backs don't last more than about 10 years. But Emmitt Smith was actually an exception to this. He lasted a solid 15 years before he retired. And so what we have here is we have his age, or the year he played, and his rushing yards for each of those seasons. And so what we want to do is we want to make a time plot with this data, and we want to see if there is any trend in his rushing yards over time. And so all we're going to do is we're going to make our axes. Okay. We're going to make axes and x and y axis. Here's our x axis and our y axis. Now, typically we're going to put time, in this case is age, on our x axis. So time is usually on our x axis and the numerical variable is on our y axis. And all we're going to do is we're just going to put his age, and these aren't numbered. Typically you're going to want these numbered. But we're going to have his age down here, and for every year that he ran, we're going to put a dot for the amount of rushing yards he had. So at age 21, he had, let's go back up. Age 21, he had 937 yards. 22, he had 1,563, and so on. And so I'm just putting a dot for each one of these. So at 21, he had 900 and I think it was 53, 37, sorry. 937, and then age 22, we're putting his values, age 23, and so on. And so what you want to do, once you have your dots, you're just going to connect them. So we're just going to draw lines connecting each of our dots. And then we're going to label our axes, and then you will obviously want to number yours as well. But we got age, rushing yards, and then our connected dots. And what we can do is we can actually see any trends that are happening here. So is it going up in a considerable fashion over time? Is it going down? Is it just kind of wavering around? But on this one, we can see that after a decent start, his rookie year at age 21, right here, he had a number of great years, and then an eventual steady decline down. He did shoot up a little bit his last season, but overall, he did have a downward trend after a few years of really good running. Um, Now, it's almost never a good idea to calculate correlation for a time plot. Okay. And the reason is because time plots don't necessarily follow trends. This one did. This one, over time, he kind of had a gradual decline. But you're usually not always going to see that because numerical variables don't necessarily, or excuse me, and let's say it this way, time does not necessarily dictate what numerical variables will do. It's usually other outside forces that cause numerical variables to change. So take this for example. This is a graph that was created by the water. It's called EPCOR. It's the water company that supplies the city of Edmonton, Canada. And what they did was they calculated the water usage um, over the period of February 28th, 2010, which was actually the day that Team Canada played Team US in the Olympics hockey. And so what they did was they calculated the amount of water used over that day. And you'll notice that this black line right here is the water that was being used. You'll notice that right here, here, and here, the water usage was really low. And then all the way up here, the water usage was really high. And you might be thinking, well, why is that? Well, it's because this is during the game, and the spikes happen at the end of the first period, second period, and third period, and then after the ceremonies and everything were over. And the reason is because, well, typically if you're watching a game on TV, you don't want to miss the game, right? So you're going to watch the game, which is where it's happening right here, here, and here. And then usually at the end of a quarter or a period, you go to the bathroom, right? So that way you don't miss any of the game. You can use the bathroom and then you come back and watch the rest of it. So that's what's happening here. It's an outside for or it's a force other than time that dictates this water usage. So it wouldn't really be a good idea to calculate the correlation between time and water usage. Um, but it's really just something outside of time that's affecting this water usage. Something else I want to point out is that you'll notice that the graph, the y-axis, starts at 300. And the reason is because they just don't have any numbers below about 320, 315 to represent on the graph. So it'd be kind of pointless to have a graph that starts at 0 and have absolutely nothing until you reach 300. The graph wouldn't even start until about right here. So you'd have all this blank space on the graph that really isn't doing anything. So if you're creating a graph, always label your axes with the correct numbers. If your numbers start at 315, maybe start at 300. If your numbers start at, 1050, maybe start at 1000. So just pick and choose those numbers correctly so that way you don't have any random blank spaces. I'm going to give you a second to read this. So if you need to pause your video, go ahead and do so now. Okay, so we're going to keep going. So it says, of course, this test only compares 2 particular years. The table below shows the standard deviation and winning percentages for each season from 1989 to 2009. So we've got the standard deviation and win percentages for each year from 89 to 09. And they want us to construct a time plot with this. So I've got time. Remember, time is usually on our x-axis. Time down here, and the standard deviation win percentage is here. And all I'm doing is I'm putting a dot for each year's standard deviation, and then I'm just connecting them. And so you see this one is going up and down and up and down and up and down over and over again. And it's asking us, describe any trends you see in your time plot. So if I'm looking at this, do we see, we started here, we ended here, do we see any definitive trend that is happening here? Not really, right? I mean, it goes up and then down and up again a little bit and then down a lot and then up and down and up and down and up. So there's really no significant trend between year and standard win percentage. So we can say there is no clear increasing or decreasing trend. And then explain why it wouldn't be a good idea to calculate the correlation for these data. So remember, numerical variables aren't really affected by time necessarily. Usually they're affected by other forces, like in the example we had with the with the water usage. The water usage was dictated by whether the game was being played or not. If it was a commercial break, people tended to use the bathroom more. Not necessarily time was a factor. So we can say it would be inappropriate to calculate the correlation because there is no linear trend in the data. Time isn't really affecting standard win percentage all that much. So for time plots, you need to know how to make one. You need to know how to label your axes correctly. You need to know how to describe one, such as question B right here, describe any trends that you see in the time plot. And then you also need to know why it would not be a good idea to calculate the correlation for these, typically because there's not really a clear trend in time plots. So that's about all you need to know for time plots.